Hi, this is Ken Johnson for another episode of SecCast. In this tutorial, we discuss and demonstrate two separate categories of injection flaws and show how these issues manifest in the Ruby on Rails framework. First, we will discuss and explain the concept of SQL injection, and then command injection. We will show how these problems manifest, demonstrate the risk, and explain preventative measures. There are other injection categories in existence, and to review those, we recommend visiting OWASP's injection page via the link provided under the references section of this video. The first topic we will explain is SQL injection. SQL injection, much like other forms of injection, is a problem that occurs because data and code are commingled and interpreted by other software, in this case a SQL server. If user-supplied data is unsafely used as part of a SQL query, this provides an attacker with the ability to manipulate the intended SQL query. If the attacker has the ability to run SQL syntax or code on the SQL server, this can be a very dangerous situation. How does the confusion occur? There is more than one way this can occur, but let's start with the most basic example. We'll start with string concatenation or interpolation. The concept is fairly simple. Imagine you have a string which represents a SQL query. Then you interpolate or concatenate user input into that string. Then send the string query to the SQL server to be interpreted and executed. This means user-supplied data is directly within the SQL query, giving an attacker the ability to add raw SQL to that string, which is then sent to the server and executed. This is why parameterized or prepared statements are preferred over string concatenation or interpolation. The query is first sent to the server with question marks in place of the actual user-supplied data. To the server, this means, here is the only query I want you to run and nothing else. Wait a moment and I'll send you the data that you need for this query. There's no confusion in this scenario. The server knows what query to run and then executes it once it has received the data. Alternatively, with string concatenation or interpolation, the query can be modified before being sent to the server and can be shaped to fit the attacker's needs or goals prior to interpretation and execution. Let's demonstrate this concept in action. If you are not familiar with burp or the concept of an intercepting proxy, I'd recommend watching our Intro to Burp video. To summarize burp, it is basically a locally listening intercepting proxy. Really, all this means is that we can catch and modify the requests that are coming from our browser and forward those requests onto the web application. On line 34 of our user's controller file, we have a SQL statement where user input, which is supposed to be a user ID value, is interpolated into the SQL query string rather than having been parameterized. Basically, user input is unsafely placed into the SQL query string, allowing the attacker to modify the SQL query. So we'll go ahead and initiate a profile update. We catch the request in our intercepting proxy, burp. We'll place a single quote after our user ID and inspect the response. You can see that the response has a 500 internal error indicating we caused some mischief on the server, but the error shows that our input has actually been placed directly into a SQL query, and that we can enter a new query and comment out the rest. This is, in essence, basic SQL injection. This time, we'll navigate back to the code and comment out the vulnerable SQL query. Instead, we'll leverage a parameterized query which separates the user-supplied data from the actual query. The question mark in the query signifies to the SQL server that this is the query we want to run, but we don't know what the user's data will be yet. Either way, the query and the data are completely separate, and the user cannot append to the query a new set of SQL instructions. In this case, SQL injection has been prevented simply by parameterizing the query. The next scenario we will talk about is when ORM methods behave differently than expected. Specifically in Rails, this means ActiveRecord methods. Under the references section for this video, you can find a link to railssqli.org. This site is incredibly useful for showing those ActiveRecord methods which can be called unsafely and result in SQL injection vulnerabilities. One method of interest, because of its common usage and potentially dangerous consequences, is pluck. Let's show why the pluck method, if unprotected, is unsafe. The railssqli.org website is a must-read for all Ruby on Rails developers. It provides a wealth of information on active record methods that are inherently unsafe, as well as those which can be used unsafely, along with examples. You can download the Git repo and try exploiting these weaknesses for yourself. As you can see, there is really a lot of information here. We'll want to show an example of one of these methods which is inherently unsafe. That method is called pluck and is used quite frequently. To show the columns that are available in the paid time off database table, we'll call paidtimeoff.all.first. You can see columns such as sick days earned, PTO taken, and user ID. The traditional usage here is to give a column name to the method. In this example, we show paidtimeoff.pluck params column. The params portion, of course, representing user input. So we'll say paidtimeoff.pluck sick days earned. We are returned all the sick days earned column values from this table. The caveat with pluck is that it also accepts raw SQL. This time, we'll enter paidtimeoff.pluck passwords from users hyphen hyphen. If you look at the raw query, it executes a select passwords from users and then comments out the rest of the query so that it won't break. The function returns all the hashed passwords of our users. Clearly a dangerous problem to have. How do we fix this? In this case, we are going to create an array containing acceptable column names. Next, we'll create a variable called user input, which, as you might have guessed, represents user input. Its value is sick days earned. Then we simply say, if the list of acceptable params has this user input within it, then we will allow the user's input into the pluck method. This is a very simple way of preventing raw SQL from ending up in your query. The next and final example of SQL injection that we will show is string interpolation within scope methods. The same sort of rules apply, but this is another often overlooked and area ripe for the introduction of SQL injection vulnerabilities if used unsafely. Additionally, we will show exploiting the SQL injection vulnerability to demonstrate impact. In the analytics model, we have a scope method named hits by IP. We take user input and directly interpolate it into the method. The user input is defined by the variable named col, short for column. The idea is that we can search through our analytics by a specific column name such as IP address, refer, and user agent. We'll enter an IP and check the IP address column. We catch the request in our proxy and modify the parameter from the IP address column to asterisk space from space users hyphen hyphen. When we forward on the request, you can see that the response is parsed and rendered within our data table. We've received back all the attributes of all of the users in the database, from email to administrative privileges, password hashes, and authentication tokens. Now we can authenticate to the application as any user because we have access to their authentication tokens. Again, using a parameterized query and/or whitelisting user input could have prevented this issue. Prevention is fairly simple. Here are our recommendations. Familiarize yourself with the unsafe use cases with ActiveRecord using railsqli.org. Leverage parameterized queries versus string concatenation or interpolation. And whitelist user input where inherently dangerous methods such as pluck are used. Only allow user input if it matches a predefined list of acceptable parameter values. Command injection is similar to SQL injection, except that the server interpreting and executing the string, which represents a command, is executing it on the web server versus a SQL server. These are system-level commands and are inherently dangerous. Even when safer forms of system execution with user input are used, there is still risk involved. Unless absolutely necessary, I typically recommend removing this behavior. If required, there are steps that you can take to secure this type of functionality. The first step is to leverage a whitelist with user input, and in addition to that, leverage safe versions of methods such as system, which allow for a pseudo form of parameterization. Again, both steps would need to be taken in tandem. One without the other is ineffective. There are 4 common ways system commands are executed in Ruby: backticks, exec method, popen method within IO class, and the system method. First, let's show what happens when user input is interpolated into a system method call. In our benefits form controller, we have an action named upload. The file to be uploaded, as well as a parameter named backup, which has a true or false value, are sent to the benefits model save method. The save method has a caveat that if the backup parameter is true, it will call the make backup method. Within that method, we make a system call in order to create a backup file. Unfortunately, we take the name of the file and directly interpolate it into the system command. First, we check the files and folders in our directory. Note a lack of the "this is a test" directory. We'll choose a text file and upload it. We catch the request in our proxy and change the backup parameter from false to true so that the make backup method gets called by the application. Additionally, we will change the name of the file from test.txt to test.txt semicolon. For those that are unfamiliar, this tells the system that you are going to send more than one command, and then we give a command to make a directory named "this is a test." We'll forward that request along and take a look at our file system structure again. As you can see, we now have a directory named "this is a test," indicating our command injection attack worked. Obviously, more nefarious things can be done here, like moving your secret token file into the public directory, removing files, and give an attacker remote access to your system. In order to fix this type of issue, we can use parameterization. In this instance, we can actually use the file utils method cp if we wanted to, but for demonstration purposes, we'll show using the parameterized version of the system method. Remember, even if using a safer version of a system command method, whitelist user input or remove the functionality altogether if it isn't absolutely necessary. From the Rails console, we'll execute a system command. We'll perform an ls command, append a semicolon so that a new command can be formed, and use the command uname. Once executed, you can see both a directory listing as well as the Unix name of our system, Darwin. Let's try this again in a parameterized fashion, where we place commas in between each individual command to be executed. Note that this command does not work because it prevents us from unsafely ending the previous system command and beginning a new one. Let's try something more normal, like listing the public directory using this parameterized version. You can see it executes successfully. So normal behavior works, but abnormal behavior is prevented. To recap, we've discussed SQL injection and command injection and demonstrated the flaws, their impact, and how to prevent them. I'm Ken Johnson. This has been another episode of SecCast. Thanks for watching.